All right, for this next example, so I skipped example 4, so you can do that on your own. You have already the answer key, but let's start with example 5. So for example 5, you have a steam condenser that receives this mass flow rate of steam with an enthalpy entering of 2570 kilojoule per kilogram, and then steam condenses into liquid and leaves with an enthalpy of 160 kilojoule per kilogram. So cooling water passes through the condenser with a temperature increase from 30 to 24. Calculate the cooling water flow rate in kilogram per second. So just imagine this diagrammatically, no? So let's create a diagram that shows this problem, no? So in a condenser, the objective of a condenser is to condense, no, the steam. So you have a wet, no, or saturated region, no, state of this steam that could be entering in this point here, and then leaving in this direction, no. So you have this entering and then exiting. Okay, and then let's write everything pala, no. So the mass flow rate of the steam is 10 kilogram per second. And then the entering enthalpy is 2570. So I'll just use H2 here since this is the most applicable notation. So H2 is 2570 kilojoule per kilogram since this is zero point 0.2 in the Rankine cycle, right? And then the enthalpy leaving is 160 kilojoule per kilogram for the steam. And then you have again a cooling water, no, that condenses the steam. So you have a higher energy. Sorry, I didn't write H3 here, so I'll just write H3. So this is H3. So you have a higher energy, no, to lower energy means basically the internal energy has decreased, no. So we can change that, no, with a cooling water, no. So what happens is you have a heat exchanger right here. Usually water, no, because it is easily accessible, no, it is easy to use to yung water natin. So the entering temperature of the water is 13 degrees Celsius, no, and then you have 24 degrees Celsius. Okay, so we want to know what is the mass flow rate of the water, no, entering here, no. So what you can do is do an energy balance here. Okay, so they are not in direct contact, so the mass is conserved directly here, right? The mass is conserved directly here, so there is no direct interaction, or they are not mixed. So if you do a mass balance, you won't get anything, but they will just have the same mass input and outputs of the steam and the water respectively, or the cooling water respectively. So what you have to do is just energy balance. Now, if you do an energy balance here, you will see that the mass, no, so energy in is equal to energy out, or the energy received, no. So you can just write here the energy received or energy rejected by the steam, no. I just write here in delta E steam, and then the energy that is absorbed by the cooling water, no, is equal, no? So the change in energy in the steam we have here from 2570, no? I think I'll just write in letters, no? So ms H2 minus H3, no? Right? And then this is equal to the change in energy of the water, no? So you have the cooling water, and then you have the change in temperature, no? And then Cp. So since this is only I mean we have a cooling water, we can just use basically MCP delta T, no? So MCP and then delta T. So then change in temperature, you have I'll just have this as TO minus T in, no? Okay, so we have everything given, right? So this is given. CP is given 4.187, and then TO and TN. Sorry, this is what we're looking for. So we can find the mass flow rate of the water, no? So mass flow rate of the water can be found. So I guess I'll just write this down first, no? So you have MS H2 minus H3 over CP and then TO minus TN. Okay, so the mass flow rate of the water is equal to, so we have 10 kilogram per second. You have 2570 minus 160 and then divided by CP. So I'll just use 4.187. So this is kilojoule per kilogram Kelvin. And then TO minus TN. So this should be absolute temperatures, no? Talking about temperatures, you should convert this into absolute, no? But in certain cases, no, if this is a difference in temperature, a shortcut, it might do naman, no? Pwede naman kahit diretso na kapag temperature difference, no? Okay, so you have 24 minus 13. So mass of the cooling water, you have here, that is 10, so 2570, and then minus 160, then 4.187, and then 24 minus 13. Okay, so the answer is 523.26. So 523.26 kilogram per second of cooling water, no? Ayan. Okay. All right. So you can check the units, no? So this should be in kilogram per second. This is kilojoule per kilogram, right? So kilojoule, just write this down here. So this is in kilojoule per kilogram Kelvin. This is in Kelvin, no? Difference in temperature is usually in Kelvin pa rin, no? So this will cancel out, cancel out, cancel, cancel, Kelvin, Kelvin. So it will be in kilogram per second. Okay. Another thing to take note maybe is that um in some cases we want to find what is the ratio of the mass of the steam versus the mass flow rate of the water, no? So in some cases you have to just find the ratio, no? How much steam, no? How much mass of the steam versus the mass of the water, or conversely, no? You have the mass of the water over the mass of the steam. So that you can find the ratio needed, no, to operate your power plant. So let's say you're operating at 10 kilogram per second, so you would need 523.26. So basically, you can divide their values to find the ratio, no, needed. So you have 523 over 10. So you have 52.20 to 236, no, kilogram of water per kilogram of steam, no? Or water, we make cooling water, no, because they are both water. So in some cases, let's say you want to operate your power plant at 1 kilogram per second, so you only need 52 kilogram, no, of cooling water, no, per second. Let's say you want to operate at 2 kilogram per second for steam, then you just multiply this by 2 and so on. So this is the same with air fuel ratio, no? Okay, I think that's it. So thank you guys.